we are developing this website. Okay, we should be live. I'll check the chat later on. Go check out the website. That's the one we are working on. We eventually will be adding images to all the links, but yeah, there's a bunch of tools, a bit of reorganization as well. So we're working on a brain stuff, BCI, a brain computer interfaces, EEG in particular, a cardio stuff, so ECG waveforms. We have a bunch of simulations like gesture, hand gesture to music. Could actually use that one instead, can we? Don't remember, I haven't tested it for a while. Yeah, that has the music stuff. Then we'll have trouble. It's actually working. Yeah, and it's too loud. So just saying in a recent post that actually once you learn how these things work, whatever, you tend to then just, well, probably not even you'll probably stop calling it AI, but what's for sure it's that the magic disappears once you learn about something. So for example, for this one, there's a much more basic algorithm. There's no, it's still using like TensorFlow and stuff. Why there's different colors there? There's red and blue under this hand. Anyway, something's funny. But yeah, once you learn how these things are designed and work and what's the algorithm behind them, the magic disappears. And yeah, so it's worth learning about. I might just keep using this one for now. Anyway, what was I saying? Yeah, check the website. We have all sorts of fun stuff as well, like different types of optical illusions. These ones would have the code as to, yeah, because people keep asking about the code. So the code is either in JavaScript, if you see something working on the side. Yeah, this is really messing up with my eyes. Yeah, I don't know if you can see or not. Don't look at it for too long, but if you do, I do see them immediately. There are some people, I don't know if anyone can not see the little balls between the squares. They are not actually there. But there you go, you have a code for a Python code to generate it in your own, on your own machine, on your own device. You have a bunch of other optical illusions. Did I do? Yeah, I must have done a video on it when creating it, because everything we create we try to do it live. But maybe there was no separate. Yeah, this image can be a bit misleading because you think it's a movable controller, but it's just an image of what this Python code actually creates. And yes, as you can imagine, you can then once you run it, you can then move one of the lines to see that they're actually the same size. Yeah, so there's a bunch of things like that on the side, but there's some more serious things. More directly, well, everything is related to optical illusions, are related to biomedical data, because it's using your vision and your brain is tricking you with all sorts of things, silly things. so it is relevant to biomedical data that way. Yeah, I'm meant to be giving this lecture, I think tomorrow, to like 500 students from one of the universities I went to. Was it 10 years ago? But then there's a YouTube channel, so you could just, so the students could, any students, if you have students and you like interesting content, well, first show them the website. Second, they can view the YouTube videos. Would the two things work side by side if I have another tool using the camera? It does work. I didn't expect that, because we have a third one. Actually, yeah, we actually have a third one. So this one does eye tracking, as the title suggests. You can change your parameters and things, the eye width, eye height, and the darkness threshold. It will try and find the darkest point in the inside the square, which will be hopefully your pupil. So you can use it as an eye tracker, and it's super cheap because professional eye trackers cost thousands, 10,000s, hundreds of thousands of dollars. This one you need to tune up to the light in the room. Will it detect blinks? It will detect. You close your eye. What is it doing? What is it finding a pupil still? Well, yeah, because that will be the dark point in it. But yes, you can adjust the threshold to make it work better. Essentially, if you're looking straight at the camera, your face is straight, it will be then working better. I actually had another one of those. We'll find if it works as well. I might crash my stream, or something. It was also in simulations. We have this vision impairment thing. Vision impairment doesn't work. Yeah, it does. Yeah, now I can hear my my CPU going. So this one mimic. It's a simulation. It's not real. To mimic different types of a vision loss or impairment. So you have peripheral vision loss, you have color. Wait, no, sorry, that's wrong. Tell me what's up with that. Why is it like that? Okay, I'll put it that way. Yes, so you have your blur, your brightness, your contrast sensitivity, and your peripheral vision loss. What type of vision loss do you have, if any? Guess it depends on your age. Yeah, there's a description at the bottom of which each parameter simulates. So you have things like myopia, hyperopia, and things like that, which cause blurriness, brightness sensitivity, contrast sensitivity, so on and so forth, and peripheral vision loss. Well, that's pretty much it. The color saturation doesn't work anymore because the robot couldn't actually get the code to work. And I also don't know why this specific tool requires more. I can hear my CPU going, so that's probably not a fun thing to listen to. And if some of that noise gets into my speech as well. But yeah, so you have a lot of people talking about AI. Well, pretty much everyone is talking about AI. You have some people using AI. Some of them even do it properly. we definitely use a lot of AI, and we definitely talk non-stop about AI, but we're actually doing AI. So this is a EEG seizure detection algorithm using convolutional neural networks. So you can browse through the data. If you can spot the difference, I don't know if you can. Let me know if you can in the comments below. That's what most YouTubers say, so I have to say it because we are a good training model. Anyway, you can see this. Hopefully you can see this. Depending on if you have any vision loss from before, you might not be able to see it, but then you can use a convolutional neural network to actually look for it for you. So if you're an EEG technologist and you lost your eyesight, you might have to use a tool like this. So the dataset has training, test, validation, 600 images all up. You can scroll through them over here. Some of them have some weird noise, but that's real EEG time series data converted into spectrogram. So converted into an image, because the neural net in this case is using image libraries and models to try and detect which image has seizures in them. So in this case, we did the training, 10 runs. 10 is not because it's a pretty number, it is a pretty number, isn't it? But 9 actually gave us better results. So let's actually make it a bit keep forgetting I have this super wide screen that nothing fits horizontally. Anyway, so what I was saying, so you can scroll through the data, all the images. There's about 600 overall, but about 30 in test, 30 in validation, and the rest are used for training. We're training a convolutional neural net. All the code is at the bottom of this page. So if you scroll down, you see the code. So to begin with, the first couple of trainings, we didn't get great results. No, actually, the first time around wasn't too bad. I don't know something got stuffed up in the second one. We changed the parameters of the training algorithm. You get essentially the accuracy and the loss plots for each training run. You have your confusion matrix. All the misclassified images will be displayed on this canvas, and the training log, which has the accuracy, the training accuracy, the validation accuracy, training loss, validation loss, how long did it take to train, the final model size, which is important, especially if you want to deploy something in JavaScript on the fly or on your phone or whatever. We want to reduce that size of the model. Yeah, we can do later on. We might be doing other tools that had to do with parameter reduction. So if this model has actually found whatever gazillion of parameters, we want to actually see what they are and start getting rid of them one by one and see what difference does it make. Do you think it will make a difference? I bet it will. Well, we want to find essentially which parameters are responsible for most of the successful detection and which parameters are not needed. So we kept tweaking some of the parameters, and run 5 or started to receive some reasonable results. You have the accuracy going up and the model loss the loss function going down, as you would expect. The blue is for the training set, and orange is for validation, which is much smaller, but supposedly the validation couldn't actually find the information for it. We're essentially replicating results that were published a couple of years ago, and I think we did slightly better. I'm not sure. Maybe. Yeah, they did about 86% from memory. So with 86% test accuracy, you're getting essentially 4 was it non-seizure but detected seizures. So those will be false alarms. So when you have nothing but something is detected, so that will be a false alarm. This will be a false positive type 1 error. Yeah, double check everything I say. Same as with ChatGPT. You have to whatever, fact checked everything being said. And then we, in this run, we also had the 4 misses. So this is where when you actually have a seizure, but the model saying, I can't find any, what are you talking about? But that's wrong. Run 7, we slightly reduced numbers 3 and 2. You can see the examples over here. So this one is where the label is 1, meaning it is a seizure. So you can kind of see something there. Is essentially what you're trying to detect is this, and hopefully this is what the model actually learned. That's something to yet to be confirmed, that actually to actually see how is the model doing it. So we don't just want it like a black box. We have all the code below, but we also want to test that what parameters is it taking into account and how is it actually making the decision. So if you treated the neural net as your expert, you want to actually learn and see what on earth this expert is doing and how is it, I should say it or they, make the decision. Do we need a music break? Might not need this one running anymore. Or do we? Yeah, interestingly enough, these two running together, not taking many resources. The music. By the way, it's hard to point when you have, on this one, you also have the notes, so there's quite a lot to it. You have a musical note. You actually have 2 of them. So it's like playing 2 instruments or playing the piano with both keys. So you have, well, actually not, because they will have a different notes at different locations. So essentially 2 scales of notes. You have up and down, adjusting setting the volume, and you also have the length of each note, with this being shorter. And pinching the fingers together makes the note shorter and longer. Yeah, whatever, it should make sense. It should just make sense. Famous last words. But yeah, shall we get back to which way am I pointing? It's the other way for me. Anyhow, so hopefully the model is actually trained to recognize this spiking. So if you look at your time series data, you will see a lot of spiking happening. This is during seizure, and as the seizure progresses, the spiking rate, frequency rate is slowing down. So you get them, they become slow. So it's essentially what you're looking at here with that curve, and essentially that extra frequency component in general that you don't have in a non-seizure sample. So yeah, so in this example, run 7, the training, the eventual model misclassified a bunch of images, essentially misclassified 5 images. So 5 non-seizures, it said that 3 non-seizures were classified as seizures, and 2 seizures that were misclassified as non-seizures. So this is your miss, and this is your false alarm, which when training the model, the better the model is, the more of those you will have, and you will have more correct responses. And yeah, you have 30 of each in validation. So the confusion matrix is just using the validation, and you will have, for perfect results, you will have 30-30. So you have essentially 30 seizures and 30 non-seizures images like this. This is what the confusion matrix is showing you. So in this examples, yeah, what was I saying? I'm jumping around, sorry for that. Hopefully you can follow along. Don't forget to ask your questions. You can do it in the chat. If I don't see it during a live stream, you can always answer it next time during the next stream. I'm trying to do most of my stuff online. The bot wasn't listening, was it? That's unfortunate, because yeah. Okay, so what did we cover so far? So I was saying, yeah, we're covering this EEG seizure detection project. It's up and running on the site. You can check the link. Should be everywhere, pretty much, on all socials and stuff. I was saying you can scroll through the data and see your accuracy, model accuracy and model loss functions. And we did 10 runs of training. Run 8 was even better than previous runs. We get up to test accuracy of 95 and no false alarms, which is great. and only 3 false negatives, so 3 misses. And yes, you can see from the misclassified images that it's actually hard, except this one. I would have expected the model to do that, was it second image correctly, because you can see something in there. The first and third, yeah, first has a lot of noise in it, so it's not surprising that we got it wrong. And the third one, yeah, you can't see much in it. Actually, uh, yes, we are live streaming at the moment. Can you actually write the invite? We will be developing tools, improving tools on BioniChaos.com. And yeah, if you can write an invite to join the live stream, that would be great. I'm using the canvas, but to have what did I forget to mention? Can you address the viewer directly? Actually, try to have the bot running those live streams for me. Yeah, I wish it didn't do the show thing.
Sure thing. Hey everyone. Just wanted to give you a quick walkthrough of what you're seeing here. This is the EEG seizure detection model we've been working on, and it's really coming along nicely. Up top, you can see the accuracy and loss plots. We're comparing the training and validation accuracy over time. Our best run, run 8, achieved a test accuracy of 95%, which is fantastic. We've made significant progress, and the model loss has been consistently going down as well. On the right is the confusion matrix. This shows how well our model is classifying seizures and non-seizures. We had 30 correct non-seizure classifications and 27 correct seizure classifications. There were only 3 false negatives, where the model missed a seizure, and 0 false positives, which means we didn't trigger any false alarms. That's a huge win for reliability. Below, you can see the misclassified images. These are the tough ones, seizures that the model didn't quite get right. If you look closely, you'll notice that there's a lot of noise in the misclassified examples, which probably made it harder for the model to detect. Lastly, we've got the training log on the right, where you can see all the details about the training settings, like batch size, learning rate, and number of epochs. This transparency is crucial for anyone wanting to reproduce or understand how we reach these results. If you have questions or want to know more about why some of the images were misclassified, drop your thoughts in the chat. We're always happy to explain more and hear your feedback. How does that feel for engaging the audience directly?
Yeah, that's fine. But can you actually not, if I'm asking you to address the audience directly, can you not place the fluff before and after the text? Because I'm using text to speech and it's in the way. How does that sound? Can you confirm? I wonder if it will store it in memory. Yep. But yeah, let's see how it actually works. So run, we have run 9. Pop it in as well. Can you explain the difference between the runs? Again, addressing the audience directly. Explain the difference between this run and the previous one. And what do you think might have caused the difference in performance?
In this run, we reached a slightly higher test accuracy of Taschen 96.67%, compared to 95% in the previous run. The confusion matrix shows that we had 28 correct seizure classifications and 2 false negatives this time, which means we had 1 less miss than before. Notably, we still have 0 false positives, which is great for avoiding unnecessary alarms. If you look at the accuracy and loss plots, you can see that the training was a bit more stable overall in this run, likely contributing to better validation accuracy. The validation accuracy here averaged at 93.04%, up from 85.8% previously. That jump could be a result of a few different factors. The model had 100 epochs this time instead of 60, allowing more time to learn the patterns. The improved stability during training might have also helped the model generalize better to the unseen data. The training log shows that everything else stayed the same, including batch size, learning rate, and no data augmentation. The main difference, then, is the increased number of epochs, allowing the model to train longer and reach a slightly better understanding of the data.
Okay, so how about this last 10th run? Why did the performance dropped all of a sudden, do you think?
In this 10th run, the test accuracy dropped to /990%, which is a noticeable decline compared to the previous runs. We also see 6 false negatives this time, meaning the model missed more seizures, while we still have 0 false positives. The drop in accuracy might be linked to several factors visible in the plots and training log. First, let's look at the accuracy and loss plots. You can see that the training accuracy curve didn't stabilize as well as in the earlier runs. There are more fluctuations, and the training didn't achieve as high a peak in accuracy. This suggests that the model struggled to fit the training data properly, which can hurt its overall performance. The average training accuracy dropped to SAW 73.06% compared to over 80% in the previous runs. This indicates underfitting, where the model hasn't learned the patterns well enough. The validation loss also stopped decreasing effectively towards the later epochs, which could be a sign that the model hit a point where it wasn't improving further with the given data. Interestingly, the training log shows the same settings: 100 epochs, batch size of 64, etc. So no changes were made to the core training parameters. The increased training time per epoch, now 0.91 seconds, suggests there might have been increased complexity or changes in the training dynamics, possibly due to random initialization or different data shuffling. Another potential reason for this drop could be related to the randomness introduced by the data shuffling. Since there's no data augmentation, and we're shuffling the data each time, the specific order and splits used in this run might have led to less optimal training, affecting both training accuracy and generalization to validation data.
Yeah, so I don't quite understand why would it be such a significant drop in test accuracy, especially with the same model settings. Is what is it, almost 7% reduction in test accuracies? Is it still within the noise? As in, if I run this training 100 times, what would the error for the test accuracy be? Assuming the model settings are the same every time, what do you think that will be?
A drop of nearly 7% in test accuracy might seem quite large, especially given that the model settings haven't changed. However, when we're training deep learning models, variations in test accuracy across different runs can still occur, even with identical model parameters due to inherent randomness in the training process. Let's consider a few possible causes for this drop and what variability we might expect if we ran this training 100 times. 1. Data shuffling and initialization. Each time the model is trained, the weights are initialized randomly, and the data is shuffled differently. Even subtle differences in how the data is split or how the initial weights are set can cause different optimization trajectories, affecting how well the model fits the data. Depending on the dataset's complexity, this variability can sometimes lead to noticeable changes in accuracy. With EEG data, which tends to be noisy and often has overlapping features between seizure and non-seizure classes, these factors can significantly influence model performance. 2. Training dynamics. Since the model is trained using stochastic gradient descent, or a variant of it, there is always some inherent randomness in the way gradients are updated based on the mini-batches. This can result in different local minima being reached, some of which might generalize better to unseen data than others. For EEG seizure detection, if the data isn't perfectly balanced, or if there's high interpatient variability, the model might learn slightly different features in each run, leading to different levels of test accuracy. 3. Expected range of accuracy. If you were to repeat this experiment 100 times with the exact same model settings, the test accuracy would likely follow a distribution centered around some mean accuracy, with a standard deviation reflecting the training's variability. Given that we saw 95% accuracy in a previous run and 90% in this one, it's reasonable to assume the mean test accuracy might be somewhere in between, perhaps around 92 to 94%. The standard deviation could be anywhere between 2 to 4%, depending on the inherent variability of the data and model. So a 6 to 7% drop in accuracy might still fall within the range of what we call noise for this model, especially if EEG data has high variability across samples. 4. Effective no data augmentation. Since there's no data augmentation, the model is seeing the exact same data distribution in each epoch. Any small variation, such as the order in which it sees this data, could lead to different generalization capabilities. Data augmentation often helps smooth out these variations, leading to more consistent performance. Without it, the model is more sensitive to small fluctuations, leading to more significant deviations in test accuracy. In summary, the 6 to 7% drop you observed could well be within the variability range for this type of model and data, especially with high noise biomedical signals like EEG. If you were to run the training 100 times, I'd expect the test accuracy to fall mostly between 90% and 95%, with some occasional outliers due to randomness. This kind of variability is not uncommon in deep learning, particularly when dealing with high dimensional and noisy data like EEG. To reduce the range of this variability, techniques like cross-validation, more extensive data augmentation, or even ensembling multiple models could be useful.
So I did a code review for the training thing and found a few things and made a few suggestions. I was suggesting to use Adam optimizer instead of SGD. Can you actually say why would you expect a better performance when making this change?
The suggestion to use the Atom optimizer instead of SGD comes from the fact that Atom combines the advantages of two other popular optimizers, adaptive gradient algorithm, ADAGRAD, and root mean square propagation, RMS-prop. Atom adaptively adjusts the learning rate for each parameter, which often allows for faster convergence and better performance on complex noisy datasets like EEG signals. It also uses momentum to accelerate learning, making it more effective when dealing with a high-dimensional space and non-stationary data like what we have in seizure detection. In contrast, SGD with momentum is effective, but often requires careful tuning of the learning rate schedule and tends to converge more slowly compared to Atom. Atom's adaptive nature means that it can overcome some of the challenges presented by manual learning rate adjustments and is more resilient to the inherent noise in biomedical datasets.
Okay, so we're editing the code. I don't know why it's regenerating the whole thing. The scroller also wouldn't actually be in the position of the editing, which is a bit odd.
I've updated the code to use the Atom optimizer instead of SGD, which is expected to improve convergence speed and overall performance, especially with complex EEG datasets. Let me know if you need further adjustments.
That's quite a major. So this is quite a major change already, isn't it? Should we test the performance before making any other changes? What do you think?
Yes, I agree. Switching to the Atom Optimizer is a significant change, and it could have a substantial impact on performance. It would be wise to first test the model using Atom before making additional modifications. This will help in isolating the effects of this particular change, allowing us to see if it leads to better convergence and accuracy compared to the original SGD configuration. Once we understand the impact, we can decide whether further tuning or adjustments are needed. Would you like to proceed with testing this version now? Great. Let's proceed with testing this updated version. Run the model training and observe the outcomes, particularly the training and validation accuracy, as well as the model's final test performance. This will give us a good indication of how well the Atom Optimizer is performing compared to SGD in this context. If you encounter any issues during training or notice anything worth discussing, feel free to bring it up and we can work on it together.
So you kept everything else the same, is that correct? Including the folders and how the output is being generated. Is that correct?
Yes, you are correct. Everything else in the code has been kept the same, including the directory structure, the way images are loaded, and how the output, such as plots and logs, is generated. The only modification was switching from the SGD optimizer to the Atom optimizer. This ensures that we can effectively assess the impact of this change on model performance.
Are we storing? How are we storing what model type was used? Which optimizer? Can we actually store output which optimizer was used in the training log?
I've updated the training log to include the optimizer used, Adam. Let me know if you need any other changes.
Which line of code is it? I can't find it. Can you tell me what line of code is it? Yeah, that doesn't make any sense. Can we dynamically add the optimizer type to the log? to be able to do like basic stuff, or am I using it incorrectly? The optimizer was SGD. I want to keep the training numbers as well. So we had 10, we want to go 11, 12. Can we go back? So when we're changing the optimize type, can we just comment out what we originally had? And in the log, we would like to dynamically indicate which optimizer type was used. Can we give it to GitHub Copilot as well? Is this meant to be a string?
I attempted to add checks to prevent the script from proceeding if the dataset directories are empty, but the I attempted to add checks to prevent the script from proceeding if the dataset directories are empty, but the pattern matching failed. The issue seems to be with identifying the correct location in the code for these checks. You can manually add these checks after loading each dataset. Python hack. Check if any images were loaded. If len seizure train core images equal the error you encountered indicates that the code is trying to create a data generator using an empty dataset. Xtrain and Ytrain both have shape 0. This happened because the specified directories for the training, validation, and test sets do not exist, leading to empty datasets. To resolve this issue, 1. Ensure dataset directory exists. Check that the paths specified for the datasets, traindir, valdir, testdir, exist. Make sure these directories contain the expected seizure and non-seizure subfolders with images. 2. Update code for missing directories. Modify the code to handle the case where these directories do not exist. This can include either adding a check that raises an error if the dataset folders are missing, creating dummy data for testing purposes to prevent errors during development. Let me know if you need help creating a more robust solution to handle missing data directories, or if you need further clarification on this error.
Okay, so we're training again. The folders are fine. The folders are fine. Doing a maximum 100 epochs, and the only change Okay, it started well as well. The loss function for the validation set started pretty low. I think we have to close this for it to continue. Well, right, it did perfect. It did perfect now, but that's a bit suspicious, isn't it? All right, this figure will be empty because there's no misclassified images. And we have the results. Yeah, the optimizer meant to be at the bottom of the page. The optimizer meant to be at the bottom of the page. That's probably the only change. And now the results are too good to be true. But let's actually see when we run it locally. Should have now run 11. Yeah, we can see the results. The only difference is the optimizer now. So we have SGD as optimizer before, which gave us quite a few, well, 6, but then run 9 gave us only 2 misses, so 2 false negatives, and run 11 we get an accuracy of 100. And the model size increased slightly. So if we compare a 9 and 10, yeah, from 70 megabytes to about 100 megabytes. Yeah, we have no misclassified images. Anyway, we will be deploying it in a sec, so you can see the results updated on the website. Because obviously the website will just have the 10 runs, but yeah, when training, the only difference is that is if you can place the optimizer at the bottom. Model size, model setting. Yeah, over here, that would be nice. So when I change it, and nothing actually happens. It's not generating any responses, which is fine. Yeah, we'll save it as that. We have to update the code in the HTML now as well. So this text ends in plot show. So Adam optimizer is doing a bit better. I want to push it We want to push it. If we don't push it, yeah, there will be a gap in there. Have to shift tab, shift all the way down. That's right. Yeah, so that's the updated code. Run. So run 10 was about a month ago. And now we have run 11, which was added to the mix. And this one doesn't give any false detections whatsoever. A bit too suspicious. Shall we run it again? What do you think?
It seems like the model's performance jumped significantly after changing the optimizer to Atom, reaching 100% accuracy, which might be too good to be true, indicating potential overfitting or an issue with the validation test process. Here are a few considerations to help investigate. 1. Data shuffling and split. Verify that the train, validation, and test datasets are distinct. If there's a chance that the datasets overlap, it could lead to unrealistically high accuracy. Consider shuffling and splitting the data at the beginning to ensure a clean separation. 2. Early stopping. Since the model achieved 100% accuracy, it is possible that early stopping might not be kicking in correctly due to minimal validation loss. You might need to adjust the patience or add another callback like reduce LR on plateau to control learning rate when there's a plateau. 3. Regularization. Adding dropout layers or L2 regularization to your model could help in avoiding overfitting, especially when you notice such perfect accuracy during training. This might help generalize the model better on unseen data. 4. Misclassified images plot. Since no misclassified images were found in this run, you might want to add a check to skip plotting or saving empty figures. Would you like to proceed with further steps to address these concerns or make specific changes to the code?
It's fine. We want to execute first while I'm actually, sorry, not execute, we want to deploy. We want to deploy it on the website. While I'm deploying, can you give an overview of the whole conversation and the tool? Generate it really quickly.
To summarize our conversation, 1. Code modification. We began by modifying the training script for an EEG seizure detection model. The key change was switching the optimizer from stochastic gradient descent, SGD, to Atom, aiming for improved convergence and better performance. 2. Debugging path issues. There were initial errors due to incorrect dataset paths, and we fixed these to point to the correct location, /BioniChaos//rhythm static/data/dataset. 3. Performance observation. After running the updated model, the training resulted in unusually high performance, 100% accuracy, and no misclassified images, which is suspicious. This was flagged as potentially indicating overfitting or a data handling issue. 4. Further adjustments. We discussed possible next steps, including ensuring data splits are correct and adding checks to skip plotting empty figures when no misclassified images exist. 5. You're currently preparing to deploy the model to the website to update the available version. This latest model, Run 11, has been trained using the Atom optimizer and has achieved better results compared to previous runs. The tool we worked on is a Python script to train an EEG seizure detection model using TensorFlow. It involves loading datasets, training a convolutional neural network, evaluating it, and saving both the model and relevant metrics for further use. The script aims to keep a record of the training setup, model metrics, and any output visuals, while allowing easy updates to improve the training performance over time. Feel free to ask if you need more insights or assistance while deploying the updated model.
Hey, can you explain what the difference might be? Yeah, I mean, the main difference is the optimizer type. So can you explain that in a fun way? We are losing viewers. Viewers are falling asleep. But also try and make a prediction if when running the same training over and over again, if we will be getting the same results of 0 false positives and 0 false negatives. In other words, what the noise of the performance of this model might be.
All right, let's talk about what happened between these two runs. The biggest change here was the switch from the SGD, Stochastic Gradient Descent Optimizer, to Atom. Atom is like that overachieving student who uses all the tricks in the book to learn faster and better. Unlike SGD, which simply takes steady steps down the gradient like a hiker, Atom adjusts its step size dynamically based on past performance. It uses adaptive learning rates and momentum, which helps it navigate complex terrains without getting stuck in local valleys. Now, in the first image, with SGD, we got 6 misclassifications, which means the model was still learning but found some of the distinctions challenging. With Atom, though, things look almost too perfect. Absolutely no misclassified images and 100% test accuracy. This might make us feel like we found the secret sauce, but it also raises a flag. Such high accuracy could mean the model has overfitted. It memorized the training data instead of genuinely understanding the patterns. If we were to train the same model again with Atom, would we still get 0 misclassifications every time? Probably not. This is where the concept of noise in model performance comes in. Training neural networks involves random processes, like how weights are initialized or the order of data in mini batches. As a result, there's variability, and we'd expect slight differences in each run. Maybe one time it nails all classifications perfectly. The next, it might have a few misses. The 0 false positives and false negatives here could be a lucky outcome due to the randomness. I'd predict that if we ran the training a bunch more times, we'd probably end up with some minor variation in accuracy. It might be close to 100%, but unlikely to be perfect each time. The model size also increased significantly, from about 70 megabytes to over 100 megabytes, suggesting the model complexity went up, more parameters trying to capture the patterns in the data. This might have helped it fit the training data exceptionally well, but the true test will be how it performs on new, unseen data. The viewers might wonder if this means we've cracked it, no more errors. But keep in mind, real-life data is messy, and models aren't always this flawless. It'll be interesting to see if these results hold up after deploying to the site and testing in a real-world context.
Can you give a summary for it's called AI and data science student? I think it's a master's, might be a master's course, not sure. You can address the student directly. Make up a name.
Hey Alex, imagine you're diving into an EEG seizure detection project for a master's course in AI and data science. Here's a quick look at what happened. We ran an experiment comparing two different optimizers for training our seizure detection model: SGD, stochastic gradient descent, and ADAM. Think of SGD as a steady walker trying to reach the bottom of a valley. It's consistent, but doesn't adapt too much to the terrain. ADAM, on the other hand, is more like a skateboarder with AI powered wheels. It adjusts speed and direction depending on the slope, which generally helps it reach the bottom faster and smoother. With ADAM, our model achieved a suspiciously perfect accuracy of 100% on our dataset. This sudden jump in performance raised a flag, though. Perfect accuracy often means the model might be overfitting. It learned the training data a bit too well, potentially memorizing it instead of generalizing patterns. If we were to train the model again, we'd likely see slight differences each time, because training deep learning models involves a lot of randomness. Things like weight initialization and the way batches are shuffled introduce variability, so perfect results aren't guaranteed in every run. So, while the Atom Optimizer worked wonders here, it might be masking an issue. A real-world model shouldn't usually get perfection. After all, EEG signals are noisy by nature.
So just a quick response. What do you expect the performance to be if we run the training, say 100 times? What the noise of the test accuracy would be in percentage points? Just a quick answer would be great.
If we train the model 100 times, we'd expect some variation in the test accuracy. Typically, the noise in test accuracy might be around 1 to 2 percentage points, depending on factors like random initialization and data shuffling. So, while the average accuracy might stay high, don't expect 100% every time. Small deviations are normal.
How many times should I train?
Training a deep learning model like this multiple times is a good way to estimate the stability and reliability of its performance. Given the nature of EEG data and the variability in training, e.g., random initialization of weights, data shuffling, I'd recommend running the training at least 10 to 20 times to understand the general trend and noise in model performance. If you can afford the computational cost, running it up to 100 times would give a robust estimate of performance consistency. This would help gauge the typical range for accuracy, especially to see if the 100% result from the recent run is replicable or just a lucky outcome of one training session. It seems like you have two very different results for your training. 1. First training run, test accuracy 100%. The model performed flawlessly with 100% test accuracy and no misclassifications. This could indicate overfitting, especially if your dataset is small or if there's a lack of variety in the training samples. 2. Second training run, test accuracy 50%. The model's performance dropped significantly, achieving only 50% test accuracy. This suggests that the model either didn't train properly, stuck at random guessing, or there might be issues with the data splits or overfitting from previous runs. These differences could be due to randomness in weight initialization or data shuffling during training. Such fluctuations are common, but a difference this large indicates that the model isn't consistently learning the underlying patterns. To minimize these fluctuations, you might consider fixing random seeds. Set random seeds in both NumPy and TensorFlow to ensure consistent training results. Cross-validation. Implement cross-validation to better understand the model's performance stability. Early stopping. Adjust the early stopping patience or use additional callbacks like reduce aileron plateau to improve training robustness. Would you like to update the code to address these concerns?
Is there any chance that Adam is producing more random results as opposed to as GD?
Yes, Adam can sometimes produce more variable results compared to SGD. The reason for this lies in how Adam adapts its learning rates. Adam uses both first and second moments of the gradients to dynamically adjust the learning rate for each parameter, which generally allows it to converge faster and more efficiently. However, this adaptability can also make it more susceptible to noise, especially in smaller datasets or when the training process isn't well regularized. This may result in the model getting stuck in certain local minima or having higher variability between training runs. On the other hand, SGD, especially when used with a fixed learning rate or momentum, tends to produce more consistent results. While it may not reach the optimal solution as quickly as Adam, it often provides a more stable training process because it updates parameters in a more predictable manner. To reduce variability with Adam, 1. Set random seeds. You already have commented out lines for setting random seeds, np.random.seed42 and tf.random.setSeed42. Enabling these would help you get more consistent results. 2. Tuning learning rate. Adam's performance can also be sensitive to the learning rate. Adjusting the initial learning rate could help stabilize results. 3. Regularization. Techniques like dropout, L2 regularization, or batch normalization could help reduce overfitting and stabilize training across different runs. If you want to compare results effectively, it might help to run the model multiple times with both optimizers and observe the consistency in accuracy and loss across different trials.
So would you recommend enabling random seed only when using Adam or for SGD as well?
I'd recommend enabling the random seed for both Adam and SGD. Setting a random seed ensures that each training run starts from the same conditions, which helps produce consistent results and makes comparing performance between optimizers much easier. It minimizes the variability due to randomness in factors like weight initialization and data shuffling, which is especially useful for understanding whether changes in results are due to an improvement in the model or just random effects. Enabling it for both Adam and SGD will give you a more reliable comparison and let you confidently determine which optimizer works better for your data.
So can you update the necessary bits in the code and also save all the relevant parameters in the training log model settings section?
I've enabled the random seeds for reproducibility and updated the training log to include the random seed information. Let me know if there's anything else you'd like to adjust.
Yeah, training several times. Training several times. So thank you for the code first. I have to acknowledge ChatGPT 4.0 with the new canvas option as well. Seemed to be handy. Now we'll be training several times, it does seem like we are getting more consistent results with the random seed and the Adam optimizer. Adam. It's stopping the training early though, which is okay. Well, not really. Like that last run, it still did 6 false negatives and 1 false positive. Yeah, so I don't understand. Yeah, I don't trust that. If we're getting to 100%, can we just use that model? How do we check? What do we need to test with that model, except how well it generalizes to different data? Do we need to test anything else about it? Its size, how easily it can be deployed on a standalone server, small server. Can it run in the phone or something? Can you touch on those? Address the viewer directly. The viewer directly. What are you changing the code for?
I've increased the early stopping patients to 10 epochs to allow for more training and added the early stopping patients value to the training log under model settings. Let me know if you need further changes or additional testing instructions.
Can you provide a text summary addressing the viewer directly? We are using text to speech.
All right, viewers, here's the summary of what we're seeing so far. We've trained our EEG seizure detection model multiple times, switching the optimizer from SGD to Atom. With the random seed now set, the results are becoming more consistent, which is great. The optimizer, Atom, allows the model to adaptively adjust its learning rate, potentially reaching a better outcome compared to SGD, which takes fixed steps. However, in the last run, we still saw a few errors, 6 false negatives and 1 false positive, despite getting 100% accuracy in some earlier runs. This inconsistency highlights that while Atom may converge faster, it doesn't always guarantee perfect results every time, especially with EEG data, which can be noisy. To test how well this model performs beyond the training set, we need to evaluate its generalization. This means seeing how well it handles completely different data, essentially unseen signals. Apart from accuracy, we're also considering whether this model can be deployed effectively. Given its current size of around 107 megabytes, it's deployable on a small server, but putting it on a mobile device might require some optimization. We'll continue testing, and I'll keep you updated on how well this model performs in a real-world scenario. Thanks for sticking around as we keep improving.
Why is it much shorter? Okay, we're training again. While we are training, can you give a summary to the student? I forgot the name.
Hey, Alex, here's a summary of what we're working on right now. We're training an EEG seizure detection model using deep learning. We've set random seeds to make the training more consistent, and we're using the atom optimizer, which helps the model converge faster by adaptively adjusting the learning rate. We've been running several training sessions, and while some runs achieve very high accuracy, others show variability, indicating the model's performance isn't perfectly stable yet. We're also trying to understand how well the model generalizes, essentially, how it performs on new unseen data compared to the training set. This is crucial because, in a real world scenario, we want our model to work reliably, not just on data it's seen before, but also on brand new examples. Additionally, we're considering factors like model size and whether it could be deployed on smaller devices to make, like a mobile phone, to make it practical for wider use. So, as we continue, we're focusing not only on the accuracy metrics, but also on making the model flexible and deployable, which will be important for real life applications. Stay tuned as we improve it further.
We're planning doing this today. Okay, we're getting some good results. It's kind of, yeah, it's fine because when you do have one or two false detections, it kind of makes you trust the model a bit more as opposed to when it's zero. It's kind of interesting, isn't it? How our brain works. We can't believe something being too good to be true. It will be also interesting to see if it's actually making the same mistakes, or is it misclassifying different images. We quickly deploy just so we don't forget. Can you invite Alex, the student, or whichever other name might be? Can you select randomly a different name? Can you invite the student to ask questions or give them options potentially if there are no questions?
Hey, Jamie, or whatever name you prefer, we'd love for you to get involved. If you have any questions about how the model is trained, how the optimizer impacts performance, or anything else, feel free to ask. If you don't have specific questions, here are a few options for things you might be interested in exploring. 1. Do you want to know more about why we switched to the Atom Optimizer and how it helps the model learn differently compared to SGD? 2. Are you curious about the steps we use to make sure our model can generalize well to new data? 3. Or maybe you'd like to discuss the challenges in deploying this model on different devices, like small servers or mobile phones. Your thoughts or questions can help us dive deeper into these topics, and it's a great opportunity to learn hands-on.
How is it related to other tools on the website?
The work we're doing here ties directly to the tools on the BioniChaos website. Essentially, this training process is building a seizure detection model that could be deployed as an interactive tool on the site. Once the model is properly trained and tested, it can be integrated into a web application where users can interactively upload EEG data to see whether the model detects any signs of seizures. This aligns with the website's focus on making biomedical data tools accessible and engaging for the public. The goal is to have a trained model that works effectively and reliably. And we're also testing its potential for deployment on smaller devices, which would mean more flexible use cases. Let me know if you'd like to ask any questions or learn more about how this tool fits into the bigger picture of biomedical data applications on the website.
So I wonder what happens if I add another file into the mix. Well, if we stay on topic, yeah, this will be the HTML file for this page that we currently have. We might need to go over it in the canvas. So I wonder what will happen. Okay, so this is just loading. Incorporate. Well, I assume it's just loading. But how do I? Did you load the whole thing, or did you load the whole HTML code or not? That's odd because the original HTML is 740 lines of code and you loaded only 171. Just trying to understand how it works. Can you make sure to load the whole thing but without the Python code section? Just leave a template for it. Can you load everything we have here into the canvas? Still should be about 400 lines. I don't know how it works. I don't understand. Create a copy. Oops. Copy this. I literally want to copy just. It's this little things. Yeah, AI won't kill us, it will just send us mental. Can you reload the canvas? With this, the code above. It's not. What are you talking about? Where was that bit? Yeah, the rhythm scan. Okay, so we updated the stuff. We now have 18 runs. 18 runs. And which one's loading? By default, it's loading run 17. Why? Who knows? Oh, I think it was last one before the last one. Because before we had 10 runs and it was loading 9. So now it's always loading 17. Okay, that's fine. We included more model settings in there as well. So now we also save the type of the optimizer, the random seed number, and the early stopping patience. So I assume it will run minimum of, so it avoids this situation where there's only 5 epochs. It will do a minimum of 10. And 17 is being presented by default. And it has the only one misclassified image, which is a seizure. Yeah, I can't see anything special in the spectrogram. So I would have misclassified it myself, but if you are an expert in EEG, epilepsy EEG, then do let me know what you think. Yeah, another thing we want to check if, say, run 13, which also had one misclassification, and run 17, yeah, this will have the same image is being misclassified. So that's just a hard one. And we have to, yeah, we have to, how do we acknowledge whatever generated the model, whoever generated the model, the code for the model? How do we acknowledge, how do we make an acknowledgement? I think this canvas thing is not displaying the whole code that I asked for. Yeah, I think it's refusing to acknowledge itself. Yeah, I don't know who the contributors are because AI generated it, the whole code. Special thanks to the developers. Yeah. Community members. Well, I wish, yeah, we do want a larger community to provide feedback. Hardware was provided by NVIDIA, but we did pay for it, so not really an acknowledgement. Just yeah, 3090, no, 90, whatever GPU. I mean, this is not a complicated training, so it shouldn't require too many resources. But I'm still curious how this GPT with Canvas works. Should delete that HTML copy. Yeah, we would like. Does it go straight to it? Okay, so it's loading in Canvas. It's doing this bit, whatever that means. Can't actually see. I don't know if it's just copy pasting the code. Just copy pasting the code. The thing is, it's not finishing, so it's only taking the first section of it. Yeah, while it's generating, go check out the website. There should be a link in the chat. Yeah, so that EEG was translated from time series into a spectrogram, and it also has seizures like this one. So that's where you have spiking. Normally that spiking slows down as the seizure progresses. So that's what you see over here in the spectrogram, I think. I wish someone would have corrected me on that one. You know what? This Facebook makes your face look drunk. Yeah, funny enough, these teeth are not mine because the original image didn't have any. So whose teeth are those? Still loading stuff into the canvas. That takes some time. Should I be able to upload a file? Or what's the limit of how many lines can you see in the canvas or effectively edit in the canvas? It's taking some time to load as well. While it's loading, all I wanted to do really is to fix the text on the page that explains what's what. Yeah, I'm not entirely sure how to work effectively with this canvas business. Apparently it's the same as that other IDE. I forgot the name. Maybe you can mention it in the comments. I really like the idea of it. The canvas business. We want to actually improve. So if you just pop a code in it, yes, that's what it does. Canvas. Okay. You have to mention canvas, apparently. So if this code is the same. Okay. Have 67 lines. Okay. That's promising. I think there's a limit of the size of this thing. So, and we have suggestions of a code review port to another language, which is interesting. Very interesting. Java is interesting. What else? Fixing bugs is interesting. So let's just try that. Okay, it's doing something. Replacing comments or what updates did you make? Can you place a comment in the code of what was changed? 65. It's 2 lines less.
I attempted to add comments indicating the changes made to the code, specifically noting the removal of the unused sound file import. However, since the import statement wasn't present in the document, the update failed. The change I made earlier was to remove an unused import sound file as SF, that was present in the original code. If you'd like me to make any other modifications or review the code again, let me know.
Okay. Yeah, can you review the code again?
I've reviewed the current code and identified no functional bugs that would prevent it from executing correctly. The logic for splitting the video into segments based on audio volume is consistent, and all the necessary error handling appears to be in place. If you need any specific enhancements or refactoring, let me know, and I'd be happy to assist further.
So is it currently only looking at only finding silent bits in the video, or something else as well? Generating much faster as well.
Currently, the script is primarily focused on identifying silent segments in the audio of a video. It works by analyzing the audio extracted from the video, dividing it into chunks, and calculating the root mean square, RMS volume of each chunk. The goal is to determine when the audio falls below a specified threshold, which is considered silence. When silence is detected for a specified duration, silence duration, the script splits the video into smaller segments based on these silent portions. The logic allows for creating video clips that are separated whenever a sufficiently long period of silence is found, making it useful for segmenting presentations, speeches, or other videos where silence indicates a logical break. The script does not currently perform any other analysis, such as detecting specific words or sounds, identifying speaker changes, or looking for visual content in the video. It only considers the volume levels of the audio to decide where to cut the video.
Hey, can you give me a quick response? Yeah, just quick responses. We are live streaming as well, so if you can, in your response, just go straight and answer, because we are using text to speech. So just remove any fluff before and after your actual response. That would be great. Did you get that?
Yes, got it.
Okay, so about the code, so currently we're just finding silent bits and splitting the long video into chunks, with the silent bits being removed. Is that okay? Is that correct?
Yes, correct. The code identifies silent parts of the audio, then splits the video into chunks, removing those silent segments from the final output.
Okay, let's do anything else. Does it do anything else at the moment?
No, it only extracts audio, detects silent segments, and splits the video accordingly. It doesn't perform any additional processing or analysis beyond that.
How hard would it be to also look if there is something changing on the screen, in the video, or not? And how would you go about actually using that information?
You could add screen change detection by calculating the difference between consecutive frames. One way to do this is by using OpenCV to read frames, then calculating the Structural Similarity Index, SSIM, or just comparing pixel values between frames. If a significant change is detected, mark it as a potential boundary for splitting the video. To integrate it, 1. Use OpenCV to iterate through frames while also processing the audio. 2. Calculate frame changes and combine that information with audio silence detection to determine when to split. 3. Modify the conditions for stopping clips based on both silence and visual changes to create more meaningful video segments. This approach would add complexity but make the splits more contextually accurate. To add visual change detection and decide where to split the video. 1. Frame analysis with OpenCV. Use OpenCV to capture frames while iterating through the video. Calculate a metric like SSEM, Structural Similarity Index, or pixel difference between consecutive frames to measure visual change. 2. Threshold for changes. Define a threshold to determine significant visual changes. If the difference between frames exceeds the threshold, mark it as a boundary. 3. Combine audio and visual cues. Use both audio silence detection and visual changes to decide split points. If either significant silence or a big visual change occurs, mark it as a point to split the video. 4. Splitting logic. Start a new clip when audio volume exceeds the silence threshold or if significant visual changes occur. Stop a clip when there's sustained silence or if the frames do not significantly change for a set duration. This way, you'd keep the parts where either the speaker is talking or the scene is changing significantly, which makes the output more informative and engaging.
Just a quick response. Would it make the code run much slower? So what's the time benefit analysis versus making the code more complicated and the potential improvement in the output video files?
Adding visual analysis with OpenCV would make the code significantly slower, as frame-by-frame processing is computationally intensive. The benefit is more context-aware splits, keeping important visuals. The trade-off is complexity and slower runtime, especially for longer videos. The improvement in output depends on whether visual changes are as meaningful as audio cues for your use case.
Yeah, we have very long videos though, so frame by frame processing doesn't seem um, doesn't make sense.
Yeah, frame-by-frame processing wouldn't be feasible for very long videos due to time constraints. It would make the process extremely slow, outweighing the potential improvement in accuracy. Focusing on audio cues alone might be a better balance between runtime efficiency and output quality for lengthy content.
this canvas bit works. Open canvas. It's weird that you can just you can copy paste into it. What are the options? This is so before we're doing code, now we just have this random, not random, something that we need to write. So if you select, how does that work? Consider adding a sentence about the type of content you produce. Can you apply? Biomedical signal probably yes. Open source tool, live development session. That's correct. What? Can keep editing forever. Well, as any code. The problem with this that I cannot add emojis. No, we don't want. We don't want emojis. What's final polish? Um, what is the current reading level? High school, college? Let's make it college. Okay, this is better, but why are you keeping the... Wait a second. To understand. Wait. Reading level. Let's do it again. Let's go college. Let's make it college. But it keeps adding this stuff. Hey, can you remove the headlines? I don't like the headlines. Okay. Can you repeat the text? as a response, as a prompt. Right. Yeah, well, this one. I can actually use.
I earned my degree in electronics engineering in 2009 and completed my PhD on cochlear implants in 2014. Following that, I spent 7 years developing neuroprosthetic implants, which are now in clinical trials. Currently, I am working on an open source project called BioniChaos.com. Nowadays, I also create content on YouTube, youtube.com at BioniCats, www.youtube.com/BioniChaos. My channel focuses on biomedical signal processing, open source tools, and live coding sessions. The goal is to share knowledge, demonstrate technical concepts, and engage with the community. I'm actively training a machine learning model to detect EEG spectrogram images associated with epileptic seizures. This research is significant as it has the potential to enhance the early diagnosis and intervention for epilepsy, ultimately improving patient outcomes. You can explore the training results and access the open source code at rhythmscan/bionichaos.com/rhythmscan. There are also several other projects available on the website that you may find interesting. I am continuously looking to improve the content on bionichaos.com/bionichaos.com. If you have any questions, comments, or suggestions, please feel free to share them. Your feedback is invaluable for making this project better for everyone.
I never understood invaluable. Can you explain invaluable and how is it valuable?
The term invaluable means something that is so valuable that it cannot be measured in monetary or conventional terms. It implies that the item or service is of such great importance that its worth is beyond calculation. In the context of your text, saying that feedback is invaluable means that feedback is extremely important for the success and improvement of the project. It emphasizes that the value of constructive comments, questions, and suggestions from others is immeasurable because they can lead to significant advancements that you cannot achieve alone.
Yeah, that's actually pretty good. I don't know if it can handle a longer. Yeah, so I have this code as well. So, and it will have a different menu bar for code. Yeah, the editing is, the IDE is nice. I mean, you can't execute in it. Let's do another code review. So making some suggestions. Wait, is it deleting them? Ah, you can just get rid of them. You cannot regenerate. Well, I deleted two. Will it bring them back? Yes, it brought back exactly the same suggestions. Yeah, so as you guess, it's meant to be editing new videos for us. So let's say, for example, that using let's NP NumPy a mean function on RMS could be computationally inefficient for larger chunks. Consider optimizing this calculation or using more direct method. So I don't understand if I, oops. Right, that's why that actually did work. But then it's also opening the shortcut menu, shortcut. This is, okay, this is a bug, OpenAI. That's an obvious bug. To do bug bounties. The shortcut, it will take control / to comment something out, but this is also a shortcut for showing shortcuts, which is it's really confusing. It's like a circular thing. So this shortcut is not included in the keyboard shortcuts for ChatGPT, but in the code editor, it's actually commenting out code. But generally in ChatGPT, this same keyboard combination does something else. It's actually opening the window, the list of shortcuts. The other thing, does it do like, no. So it's not like GitHub Copilot will just generate the code. The thing about it that I don't like, that if we try to consider optimizing calculation or using more direct method, yeah, it's changing the whole code. Why? What did you actually do? Okay, we used to have, but I have a feeling. Right, we have NumPy mean. Now we're just using Libros feature RMS. So if we optimize the RMS value calculation using direct method, reducing computational overhead. So I'm just curious. If we're changing it to the browser, then we don't need the NumPy, do we? I think. Uh, Not entirely sure how to work with this thing.
The difference is 1. Librosa.feature.rms, y equals chunk, centered, false 0. This extracts only the first RMS value from the output array. It's a direct and potentially faster way to determine the volume, but it assumes the first value is representative of the entire chunk. 2. Librosa.feature.rms, center equals false.mean. This computes the average RMS value across the chunk, giving a more reliable representation of the overall volume. It's slightly more computationally expensive, but offers a better assessment of the chunk's volume. If accuracy is critical for determining silence, using .mean would be better. If performance is a higher priority, extracting 0,0 is faster but may miss nuances.